I'll start. So, good morning, everyone, and welcome to today's class. So, we only have had one class last week, right? So, how are you enjoying this program so far? Are you liking electrical engineering? Like the little things that you have learned so far? Okay, so we'll learn a few more basic theories today, and which are fundamental laws to solve any electrical circuits. And if we have time, then we'll also start discussing the semiconductors, which are the backbone of the electronics and the chip design that we will be doing in this program at the end. So, at the last class, I think Mazhar stopped here. He talked about how we can calculate equivalent resistance of any circuit. Right? We learned about the series connection and the parallel connection of different resistors in a circuit, and we also learned about Ohm's law, right? The V equal to IR. So with that, we learn today two more basic theories, which are known as Kirchhoff's current law. There are like many pronunciations to that name. Like you will hear Kirchhoff, Kirchhoff, Kirchhoff. So these are the most like mostly used four pronunciations of these names, but the most famous way to like refer to these laws is KCL, Kirchhoff's current law, KCL, and KVL, Kirchhoff's voltage law. So with Ohm's law, these three, Ohm's law, Kirchhoff's current law, and voltage law, these three are the most fundamental laws to solve any circuit. Like whatever circuit you see in your life, you'll be needing these three theories, three laws to solve that circuit. Okay, so we'll learn these two laws today. But before that, we'll learn these small concepts. I think you have heard these things, like you have heard nodes, right? In the last class, node. Have you heard that?
I don't think it was introduced.
Okay. So I will do that. So nodes, branches, and loops. These three concepts will lead them to when you learn this KCL and KVL. So branch is like represents any element in the circuit. So in a circuit, you can have a voltage source, right? You can have a current source. You can have different resistors. So each of these elements is a branch. Okay. So if you have a voltage source, that's a branch. If you have a resistor, that's a branch. If you have a current source, that's also a branch. Is that clear? Any element in the circuit is considered as a branch.
Just
If you have any question at any point, please feel free to stop me and ask your question, right? So then node is the connection point between two elements. So like to flow any current in a circuit, you will have to connect the voltage source with the resistor. Like all the elements should be connected with each other, and the loop or the path should be closed, right? So the connection point between each two elements, right? When at that point where you connect the voltage source with the resistor, that's a node. Okay. Any connection point between two elements is a node. Is that clear? Next, we have loop. So loop is the any closed path in a circuit. So in any circuit, we must have at least one loop to flow the current, right? Because if the path is not closed, if the circuit is not closed, there will be no current flow, right? So there must be at least one loop. There might be more. So any closed path in the circuit is a loop, right? So let's have a look at this example here. So like let's count the number of loops, nodes, and branches together in this circuit. So first let's start with the branch. So can anybody tell me how many branches are there in the circuit?
6.
How do you count that?
I counted the batteries and the resistors.
Yes, you counted the number of elements in the circuit, right? Because number of elements is the number of branches. So you're correct, yeah. So we have one voltage source and 5 resistors. That means you have total 6 elements in the circuit. That means you have 6 branches. Is that clear? 6 branches. Then let's count the number of nodes. So how many nodes are there in the circuit? And try to count that. I can give you like node is the connection point between any two elements.
But also be 6.
6?
Yeah.
Is there any other answer? That's one answer. So is there any other answer?
4. I got 4.
4. Okay, let's count together. So let's start from here. So from this point, right? So this is a connection point. Is that correct? So this is the connection point between this voltage source and this resistor here. So this is a node. We can say that. Let's name that A. Now, between this node and this point, is there anything here? There is nothing. So will that be separate node or these will be the same node A?
Same.
This should be same because we define the node as the connection point between two elements. But between these 2 points, this one and this one, there is nothing. We don't have anything. So there should be the same node. So it will also be A. Similarly, these will also be A, right? Now, if we move to the next point here, this point, so will that be a separate node? This should be a separate node because there is a resistance between, right? So this is B, and there is nothing, so these will also be, these will also be. Similarly, this thing should also be, this is that right? So all of these should be the same node B. And now if we move to this point, this should be a separate node, right? Because there is a resistance there. Similarly, if we follow this line, every point in this line should be C because there is nothing between the neighboring 2 points, right? So is there any other nodes you count, or this is it? There is no other nodes, right, in this circuit. So we have only 3 nodes, A, B, and C. Is that clear, or do you have any confusion? So we have here, we have 6 branches, 3 nodes. Now let's count the loops. So how many loops are there in the circuit?
May I ask a question about
Sure,
the
sure.
node? So if I go the left one, where is the parallel connection? So you said both of them A, B, A, B. What if the registered value is different? Will this count as a different node?
That's what we will discuss here. Also, I think Mazhar talked about the parallel connection, right?
Yeah.
So how do you identify that 2 resistors are connected in parallel? If they are between 2 nodes, right? 2 same nodes,
Same nodes.
right? So to be connected in parallel, 2 resistors must be between the 2 nodes. Like there's the case here, like both of the resistance between A and B. So these 2 resistors can be different values, but when the current will flow, you will calculate the equivalent resistance, right? You can convert 2 resistors connected in parallel into 1 by using that formula 1 over R equal 1 over R1. But these 2 can be different, these 2 can be same. There is no
But the current will be same.
current will be different. I will discuss this in the next example. Current will be different, but the voltage will be same because voltage depends on the node, right?
Okay.
So you have A and B, 2 resistors are in between A and B. So the voltage between A and B will be the voltage of the 2 resistors. So the 2 resistors will have the same voltage but different current. I'll discuss that later. So here we have 6 branches and 3 nodes. Now let's count the number of loops. So how many loops are there in the circuit?
1.
1. 1 is another, is there any other answer? Loop is any closed path. So any closed path in the circuit is considered as a loop. Okay, so let's count. So this is one, you can say this is one closed path, right? So if you start from this point and travel through this path, this is closed, right? So this is one loop. Is that right? This is one loop. Similarly, you have another closed path here, right? This is another loop. You have another closed path here. These are independent closed path. So this is another loop, and finally you have another closed path here. If you follow this path, I'm not sure if you're seeing, if there's. So this is another path, right? So if we, I'll clear all these. So we have one loop here, right? So this is one closed path, this is first loop, we have one closed path here, this is another loop, we have one closed path here, this is another loop, and finally we have here we have another closed path. So are there any other loops here, like independent loops? You can count multiple loops, right? If you count this path, like this outer like loop, that's also loop, but that has another loop inside. So that's why we don't count that as loop. That has another name that's called mesh. We'll not go there, but loop is the independent loop where you don't have any other loop inside. Right? Independent. So only one loop on that path. So if you count that way, there are only 4 loops in this circuit. Is that correct?
So there is no the condition that loop has to have all the elements, or if there anything?
No,
So it could be.
there is no condition. Only like there should be a closed path. Any closed path in the circuit will have one loop. Will be considered as a loop. So is that clear? So branches, loops, and nodes. Do you have any questions on that? So if that's clear, then we'll move to the Kirchhoff's current law, which is the first law. The law states that currents entering the node, all the currents entering the node will always be equal to all the currents leaving that node. So we know current has a direction, right? Current always flows in a direction. So from the direction that is defined or represented by the arrow, from that we'll be able to know which current is entering a node, which current is leaving a node. So the law states that all the currents that enter a node will always be equal to all the currents leaving the same node. So when you apply KCL, you have to keep in mind that we'll have to consider one node, not multiple node. So one node at a time. So if you look at this node here, let's call that node A. So if you look at this node A, we have like bunch of currents entering that node. We can say like from the arrow, we can say that like I1, I2, and I3. These 3 are entering, right? These 3 currents are entering this node A. And I4 and I5. These 2 currents are leaving this node, right? So according to the KCL, the sum of I1, I2, I3, which are entering, will always be equal to the sum of I4 and I5. Okay. So that's the formula, right? If you add the number, all the currents entering, that will always be equal to the sum of all the currents leaving the node. Is that clear? Okay, so that is like pretty simple actually. So let's have a look at this example here. So we have a node P here, and you can see like some currents are entering, some currents are leaving the node P, and here you can see that like we know the value of current, almost all of them except one, which is I. We don't know the value of I, so we have to calculate the value of I here, but using the KCL, Kirchhoff's current law. So can you try to do that? So here you have to use the formula, like you have to like the sum of all the currents entering will be equal to the sum of all the currents leaving. And if you have that equation, from that equation you will be able to find out the value of I here.
Why did you use this register symbol?
So here we know the value of all the currents. That's why, because we are using Kirchhoff's current law. If we don't know the value of currents, then we will use the value of resistors and other things.
You know, like for the currents, why did you use the register symbol?
So in your circuit, you will have some elements, right? The resistor is one of the elements. That
So we're not counting that part right now.
no, currently since we know the value of current, because for applying Kirchhoff's current law, we know we need the value of current that entering and that's leaving. So we will see another complex example. This is like very simple example where we know the currents already. If we don't know the currents already, then what we need to do? Then we will have to use the value of resistors and other things. But for now, since we know the value of currents, we can like simply use the formula.
Is it 0.6 amps?
Yes, that's right. So let's see how we can actually do that. So as I mentioned, currents entering P will be equal to currents leaving P. So if you look at this, so let's find out the currents that are entering. So this one is entering, look at the arrows here. This is also entering and this is also entering. These three currents are entering node P. So if you add them, that will be equal to the currents leaving, that is 0.4 ampere, 0.5 ampere, and I. So that will be on the right side. The currents entering node P will be equal to currents leaving node P. Now just solve this simple equation. You will have the value of I, and there will be 0.6 ampere. Right? So these are very simple, just to understand the law. But you will not see any such simple examples. Later we will look at more complex examples where we will use this KCL and KVL to solve that circuit. But is that clear? Is the law clear? That you have to keep that in mind that the currents that will enter a node will be always equal to the currents, the sum of the currents leaving that same node. Okay? And that will be same node. Same node is important here. Okay, let's go to the next law, which is KVL, Kirchhoff's voltage law. So Kirchhoff's voltage law is about voltage instead of current. Here, the law states that the sum of all the voltage drops around the loop. So here, in KCL, node is important, and in KVL, loop is important. So the sum of all the voltage drops around the loop is equal to 0. Okay, so the voltage can be positive and negative, and we know that from the polarity of the voltage, right? So the sum that is mentioned here, that is algebraic sum. We'll have to consider the sign. So if the voltage is positive, we'll have to write the plus voltage of that plus and then the value, and if that is negative, we'll have to write minus and that value. Right? So if you sum or add all the voltage drops, considering the polarity, then the result will always be 0 in a loop in any circuit. So that's the law. Is it clear? So I'm saying if you add all the voltage drops in a loop in a circuit, considering their polarity, the result will always be 0. That's the Kirchhoff's voltage law or KVL. So if we look at this loop here, so if we have only one loop here in this circuit, right? A, B, C, D. If we start from A, then we'll first find this element here. So the voltage of this element will be VAB, voltage difference between A and B node. So that will be VAB. Then we have this element which have voltage VBC, and then we have this element which has a voltage drop of VCD, and this element which has a voltage drop of VDA. And if you add all these voltages, the result will always be 0. Is it clear or? I'll also talk about another example where you will have the idea how to consider the polarity of the voltages. This is just an abstract or simple representation, right? Just keep in mind that the sum of all the voltage drop in a loop will always be equal to 0. Okay, so now let's have a look at this example here. Right. So how many loops are there in the circuit?
2.
Right. So we have 2 loops here. So how many Kirchhoff's voltage law or this type of formula we can write for this circuit? 2. So Kirchhoff's voltage law will only be applicable to one loop at a time. So if we have 2 loops, we will be able to write 2 Kirchhoff's voltage law, like this type of equations using the KVL. Okay. So I'll first explain the steps how we can write KVL for a loop in the circuit. Okay, so first we have to identify the loop that we have already done. So how many loops are there? We have to find out that. So we have 2 loops. Then we have to consider one loop at a time. So let's consider this loop, and then we'll have to check if we know all the voltages of the in that loop. of all the elements. So in this case, since this is a simple example, we know all the voltages of all the elements, right? This volt is 1 volt, 5 volt, 2 volt, V1, V2. We don't know the value of V1, V2. That we will find using KVL, but we know that the voltage of this element is V1. We at least know the voltage, right? So if we have all the voltage values of all the elements in a loop, then we can directly apply KVL. And if we don't know, we will see that in the next slide. But if we know all the voltages, then we can directly apply KVL. Okay? Is that clear? So there are two types of like scenarios that can happen applying KVL. So first one is if we know all the voltages, that's pretty simple. We can directly apply KVL. Now to apply KVL or to write this equation, we will always have to like select a starting point. So we have two loops. Like first, let's consider this A B C D loop. A B C D. So this loop here. So first we have to select a starting point from this loop. Right. Let's start with A. And when you write this equation, you have to start from this point and you'll have to travel through this loop and come back at this node, at the same node that you started from. Okay, so that's the idea. So if you start at A, you'll have to travel through the whole loop and then you'll have to end at A. And when you reach A again, then you can write that the equations like the result of the equation will be 0. The sum of the equation that you write, like while traveling the whole loop, that will be equal to 0. So now try to write this KVL here. So if we start at A, what we first see? We first see this element, right? Which has a voltage of 1 volt. And you have to see what polarity we first encounter. So we encounter here, we encounter first the positive polarity here. So these voltages will be treated as positive. Plus 1 volt. Then we go to B. Now which way we should go? BE or BC? BC, because we are in the ABCD loop, right? So we will go to this direction now. Again we encounter positive first, right? So we will have plus 5 volt. Now from C we'll have to go to CD. There is nothing, so we don't need to do anything. Then we have this element, and we encounter.
Can you do 0 for CD?
Yeah, you can 0, but since you are adding 0, like 0, is there nothing? That means you have a voltage drop of 0.
0,
right? Do you know that? Like if we don't have anything between 2 points, the voltage difference between those 2 points is 0. So 0 means nothing here in this equation since we are adding all these things. Then it will go to D and then what do we see? Negative or positive?
It's negative.
We will first see negative, so it will be minus. And the voltage of this element is V1. Right? Then we again are at the point A, right? Where we started. So we have completed the loop. So now we can write equal to 0. So this is the KVL for ABCD loop. So that's how we write the KVL for like any loop. Is that clear? So from this equation you can easily calculate V1, right? That's our target. We want to find out the value of V1 and V2 from this circuit applying KVL. So V1 is just 6 volt. Is that clear?
Yeah.
Okay. Now let's do the same thing for the next loop, BECF. You can also name the loop in any way you want. You just have to follow these steps. So since we are going these directions ABCD, let's follow the same direction BEFC. But you have to do that serially. You cannot do BECF because like there is no path. BE from E to C there is no path. You have to go through F, right? So the loop will be BEFC. So for BEFC, like what should you first do? Like to write the KVL for this loop. Do you remember the steps?
Yeah.
We'll have to select a starting point, right? So that's we don't need to write that. That's for you, for your like for yours, for your easiness, right? So the starting point that you select, so you can select any point, but you will have to follow the path. You cannot go to arbitrary point from a node. So let's start with, like, you can select, let's start with E now here. Okay. Let's start with from E. So from E, which way we will go? EB or EF?
Yeah.
You can also go EB.
Okay.
That's no limitation. But here the thing that you need to remember is, like, you have to follow the path. So if you go to this direction, you have to travel to this path, and if you go to EB, then you will have to follow this path. Yeah. So after selecting a starting point, you can take any path you want, but you have to follow the loop. You cannot go from E to C directly. Okay, so let's start from E and go through E, like go through this path. Okay, so when you go to F, we first see the positive, right? Plus, so we'll write V2. Then from A to C, we don't have anything, we don't need to do anything. Then from C to B, we see negative, right? First here, so we'll write -5. Then here we'll see plus positive first, so we'll write +2, and we end up at the starting point, so we can write equal to 0. Is that clear? So from this equation, we can easily calculate the value of V2. That will be 3 volt. So can you write like simple KVLs for this type of loops? Will you be able to do that? Right. So I'll review. So this is important. So you have to first identify the loops. How many loops are there in the circuit? For each loop, you will have this type of KVL equations, one for each loop. So if you have 2 loops, you have 2 KVL equations. And to write those KVL equations, you will always have to first check if you know all the voltages in that loop. If you know all the voltages, then you can directly jump to writing the KVL equations. If you don't know the voltage, I will show the way in the next slide. And if you know the voltage, then you can directly write the KVL. And to write the KVL, you will always have to start by selecting the starting point. Right? So after you select the starting point, you just have to travel through the whole loop and write the voltage of the elements. If you encounter positive polarity first, you'll have to write that voltage as positive. If you encounter the negative polarity first, you'll have to write that voltage as negative. And when you complete the loop and end up at the starting point, then you just can write equal to 0. That's your KVL equation. And you just solve that, you will be able to find out the unknown if there is any in that loop. Is that clear? Now let's have a look at these examples here. So these are the 2 circuits. You can just have a look at the left one.
Can I go back on time?
Sure.
Sorry. So you said the loop can be A, B, C, D, 3, but we can make the whole thing as a loop also, right? A, E, F, D.
Yes.
So
No,
like this-
that's not loop. That's mesh.
That
So
is
I
okay.
mentioned, like, inside any loop, like when you call a closed path a loop, like if inside any closed path there is no other closed path. So if you consider A, E, F, C, D,
Yeah.
this outer closed path, this is a closed path. If you look at this outer closed path, there is another, like there is 2 actually closed path inside. We cannot call that a loop. But if we look at A, B, C, D, inside A, B, C, D, we don't have any other closed paths. We can have like different directions, but no other closed path with other nodes,
Okay.
right? So that's our loop.
Yeah.
So now let's have a look at this example. We'll also again have to apply KVL, and we will have to find out the value of D0. Here. So how we can do that? I'll explain. So the first thing here, we'll have to identify the loop. How many loops are there in the circuit? One. Only one loop, right? So okay. One loop. Then what do we need to check?
Do we know all the voltage?
if we know all the voltages, right? That's what the steps are, like identify the loop and then if we check if we know all the voltages. So we know the voltage of this element. Do we know the voltage of this element? No, we don't know. We just know the value of the resistance of this resistor. We don't know. To calculate the voltage of this resistor, we need to know the value of current. Right? You remember the formula Ohm's law, V equal to IR. So you need to calculate a voltage across any resistor, you need to know the current and the resistance values. You only know the resistance values here. You don't know the current. Is that right? Or any confusion? Similarly, for this resistor, you don't know the voltage. You only know the value of the resistor. Yeah. You know the voltage of this element. Okay. So can we use the like the steps that we discussed in the previous slide here? We cannot because we don't know the voltage of all the elements in the loop. Right? So what we need to do here, we will have to assume a current because we need to calculate or we need to know the voltage of all the elements in a loop before applying the KVL. So if we want to do that, if we want to know the voltage of these resistors, we will have to know the value of current. Right? So for that, we will assume a current in that loop. Here again, you have freedom. You can assume the current in any direction you want. But like I always prefer like the right direction. So that's why you can also like there is only two possible possible direction, right? One from like the one that is shown here, and another is the exact opposite.
Clockwise or anti-clockwise?
Yes. So these are the two. You can assume any of these two. Okay. So what will be the difference? Like if you assume the clockwise and if you assume the counterclockwise, what will be the difference?
Sign positive.
Yes. Only the polarity of that current will be different. For example, if we have positive current in the clockwise direction, if on anyone else assumes that the current flows in the counterclockwise direction, the value will remain the same, only the sign will be different. If the person who assumes clockwise, if he gets the positive current, the person who assumes counterclockwise, he will get the negative current. That's the only difference. Okay, so you can assume any direction you want. So let's assume this clockwise direction. Okay, so this is the second step. If we don't know the voltage, we'll have to assume a current for that loop, and you'll have to assume the direction and the value. So we have assumed a current of I here with clockwise direction in the loop. Next, we'll have to now if we have the current, since we have assumed that we have a current, so now we know the value of current. So if we know the value of current, we now know the value of all the voltages of all the elements, right? We now know the value of the voltages of all the resistors in the circuit. So now we go to the same steps again. We will have to select a starting point before writing the KVL, right? So if we select this as the starting point, A, there's this B, C, D, E. So this is our loop A, B, C, D, E. So we'll have to select a starting point. Let's start, if we select the A as the starting point, okay. Here there is a difference. There we could go any way we wanted, right? In the previous example, after selecting the starting point, we could go clockwise or counterclockwise. But here we'll always have to follow the direction of the current that we have assumed. So if we have assumed the clockwise current, we'll always have to follow that direction. So if we start at A and if we have a clockwise current, then we'll always have to follow this path, not the other way around. Okay. So then if we follow the current, we will first see the resistor. So if we like the current is entering the resistor, right? So the voltage of the resistor, will that be positive or negative? Positive. That should be positive, right? If current enters the resistor, the node it enters, that should be the positive, and the other node that it leaves through, that should be negative, because current always flows from positive to negative voltage, right? the more voltage to the lower voltage side. That's the direction of the current. You know that, right? So you should know that from the Ohm's law. The current will always flow from higher voltage to the lower voltage node. That's what defined by the positive and negative polarity. Positive has the higher voltage, negative has the lower voltage. And the voltage we see, there's the difference between those two nodes. Okay. So we first see this 16 ohm resistor. And what will be the voltage of that resistor? So when we write KVL, we only consider voltage, right? We don't consider any other thing. So you only need to write the voltage of that element. So what will be the voltage of that resistor? I into R, right? So voltage of any resistor is equal to current of that resistor and the resistance of that resistor. Is it clear or is it too confusing? So the voltage of the resistor should be, we have assumed the current is I. So I times 16. Is it okay, or do you have any confusion?
I'm
So that's
confused
the voltage
about
of the
the 25 volt there, so we're
That's another element.
so we're not counting as a voltage.
We will count that as an element. So when we write KVL, we write the voltage of each element separately, right? So we will use that. So we'll travel through the whole loop. Now we are only considering the resistor.
Got it.
We know the current that flows to the resistor and the value of the resistor. So the voltage of the resistor will be IR, I into 16. Similarly, if we go to this resistor here, since we are following the direction of the current, these will be positive and these will be negative. So we will have positive I into 14 IR. Is that correct? So if we don't understand this simple, like these are simpler, I'm saying. So if we don't understand these simple circuits, then like we'll have hard time to understand the complex circuits that we are going to encounter in the next slide. So this is important to understand this. So if you have any questions, please feel free to ask me. Sure. So we have completed this resistor. Now we have this voltage source. So what should I write for that?
Positive 10.
Positive 10, because we are first encountering the plus sign and the value is 10. So plus 10. Now this, there is nothing, then this voltage source, right? So what should I write for that?
25.
Negative
25.
25, because we are encountering negative first, negative, and the value is 25. Now we have ended up at the starting point. So you can write equal to 0. From this equation, what you can calculate? I. So from this, we'll have I into 30 and minus 50 that will go there. So it will be 15 on the right side. So I will be 15 by 30, so 0.5 ampere. So in this equation, only unknown is I. So you can just calculate I from this equation, which is 0.5 ampere. So this is the like most difficult thing for this problem, right? Writing the KVL. If you can write the KVL correctly, you can just like solve the equation, simple equation and find the answer. So is that clear to this point? Now you can look at the problem again. Determine V naught, so or V0. So the question doesn't ask you to find out the value of current. It tells you to find out the value of this V naught. Okay, so we have find out the value of I. Now we know all the value of voltages of all the elements in the circuit. So to find V naught, what we can do?
When you say the V node, what voltage are you talking about? From which node to which node?
It is marked here, this node and this node. So V naught is the voltage
It's not showing.
between these two nodes. Okay,
So
this
the
is
first picture,
two red.
this one. Top and
These two nodes are marked. So V naught is between the voltage of these two nodes. Plus and minus are also shown. So this is, you can say this is the higher voltage node and this is the lower voltage node. So you'll have to find out the voltage between these two nodes here. So for that, we will again have to go to that idea of parallel connection. So if we have two elements in parallel, one thing we know they are between the two same nodes, right? So if we have this is, for example, this R1, this is R2. So these two resistors R1, R2, they might have different value or same value, doesn't matter. But these two resistors are connected between the two same nodes. Is that correct? A and B, right? So now what's the voltage across this R1? So if we have a voltage between A and B is A VAB, for example, the voltage of this A and B node is VAB. Now, if we ignore the R2 here, for example, if we ignore the R2, what's the voltage of R1? VAB. Is it correct? Or is there any confusions? It seems like you are lost. Are you? Or so let's go back to this simple circuit. Two resistors connected in parallel, they are between A and B. Is that clear? Like whenever two resistors are connected in parallel, they are always between two nodes. So we can say R1 is between A and B, R2 is also between A and B. So if I mentioned like the voltage is always measured between two nodes, right? So when we measure the voltage, we always get a voltage across A and B. So now if we have a voltage VAB for this A and B node, that should be the voltage of R1. That should also be the voltage of R2. Is that correct? That's the rule of parallel connection. If you are confined between, so you can have multiple, you can have 10 resistors connected in parallel between A and B. All of those 10 resistors will have the same voltage VAB. Okay. So here, if we look at this is node A. Let's name this. So if let's forget this naming ABCD. So for this simple, let's name this A and let's name this B here. So we need to find out the voltage of AB. Is that correct? Can we also say that this resistor here and this voltage here are also between A and B? Is that correct? There is other nodes, but we can consider like two things are between A and B, and this V naught is alone between A and B. So they are parallelly connected. Is that correct? You have to understand that first, going to the next step. So is that correct that this 14 ohm resistor and 10 volt, these two are between A and B, and V naught is also alone between A and B? Right? So the voltage V naught will be equal to the voltage of 14 ohm and 10 volt together. These two voltages will be same. Like the voltage of this resistor here, if we call that V1, if we call that V2, this V1 plus V2 will be equal to V naught. Can you say that? Because these are parallelly connected. These are between A and B. They will have the same voltage. In one path, we have the resistor and the voltage. So the voltage will be added. And another path, we have only V0. So the voltage of those two elements So the voltage of the two paths, in one path you have two elements, in another path you have only one element. So the total voltage of these two elements will always be equal to the voltage of that other element in the other path, right? Because they are parallelly connected. Is that correct? So we will have V1, like the voltage of 14 ohm and 10 volt will be equal to V naught. Are you clear about that? So then we can go to the next step actually. So let's solve this. So we can write V0 equal the voltage of this 14 ohms plus the voltage of this 10 volt. And again here, like what direction should we follow? Like when we add these two voltages, which direction should we follow? This direction or the other direction? The direction that I draw. Why?
Positive to negative.
Because positive is marked here. So if there was no marking, we had to assume. But since there is a marking, like positive is that node, negative is that node, current will always flow from this node to this node. That's the rule of rule of thumb for the direction of current. It will always flow from the higher voltage node to the lower voltage node. So we'll and you can see that this is the same direction of the current that we assume. So for the 14 ohm, what we will get? We will get the voltage of 14 ohm as 14 times the current. What was the current?
0.5.
0.5. Plus, we are going the direction we are entering
10.
positive first. So that will be plus 10. That will be the value of V0. So if you calculate, it will be like 74. Is that correct? Okay, so I think you have understood that, and we can check that actually. So we have another similar example in the next slide. So this is like similar example here. The problem is find I and
So like 16 ohm and 25 ohm.
yes. That's a good question actually. So like if I only considered the right portion. You can also consider the left portion. That's also the same thing, right?
Same calculation.
Yes, same calculation. But there I considered the right path because that's easier, because that's
The direction.
in the same direction of the current, but that's in the opposite direction. So here we'll have to assume
But if we
the
do
negative
it,
current.
it should have the same value. That's what I'm saying. You can
Yes,
check
yes,
yourself.
yeah.
Is it right?
Let's do that. So it should have the same value. So here the current should follow from the positive and negative, and that's in the opposite direction of the current that we assume, right? So for current here, instead of 0.5, we should use negative 0.5.
Negative 0.5.
So here V0 should be the voltage of the 16 ohm, and 16 times minus 0.5. Is it clear why I wrote minus? Because in the opposite direction. And then since we are going this direction, we first encounter positive again, so we will write plus 25. If you solve that, what should you get?
70.
70. Same word. Yeah, that was a good question. I actually missed that. So you can like go either direction, but you will have to keep the direction of the current in mind. So that's the most important thing that can change the calculation. Okay, so this is another example, similar example, right? You'll have to find I first. I is the that's the hint. Like if we assume a current like this I and this I is the same, right? Because they have the same direction, you see, same direction and same value. So this I will be your loop current that we assumed in the previous example. So this will be your loop current. So assuming this current and this direction, you will need to write the KVL first, and from that you will find out the value of I, and then using that value of I, you can also calculate the value of VAV in the same way that we calculate for V0, the previous example. So I will. So can you try to solve that? Like first solve the for I, find out the value of I here. Follow the steps that I mentioned. You don't need to solve, you just can write the KVL, like if you can write the KVL, then you can easily solve. So if you, any of you can write the KVL, just let me know. And also if you have any questions, like if any of you have a question, I can also discuss in the meantime.
It's 30 plus 3i plus 10 plus 5i plus 8 plus 0.
Sorry, that's 10.
Yeah. I did like 30 plus 3i plus 10i plus, sorry, plus 10 plus 5i plus 8 equals 0. Equation.
No. You need more time, like I can write, then you can also cross check if yours is right or not. And then you can ask me also like what you have done wrong. Right, so if you are done writing the equation, then I can also write here. I've done. How many of you are done? Okay, so what is the first step? Do you remember? Applying, like before applying KVL, what are the steps? So I, like here, you have that, right? So the first rule was like identify loops. So there is one loop again, right? So there is one loop and we don't know the voltage of all the elements because there are resistors. So if we only have like voltage elements, voltage sources, then the first example applies. Otherwise, in all the other scenarios, you have the second example where we don't know the voltage. So we'll have to assume a current. And I mentioned like clockwise current. So and that matches the value of the current that we need to find out. Direction of the current that we need to find out. So value and direction are same. So let's assume this same current and same direction for the KVL. So what is the next step? We need to select a starting point. Yeah. So let's start from here. Okay. You can start from anywhere. Okay, but you will end up with the same equation. Just some elements like before, some elements after, but the equation will be same. So if we start from here, what we first see 3 ohm resistor, and since we are going in the direction of the current flow, so it should be plus I times 3, right?
Yeah.
Then we have, what should we write?
Minus.
You will tell me, I will just write.
Minus 10.
Minus 10, 10
I times 5.
plus I times 5, then
That's 8.
plus
5.
8, then
Minus 30
minus 30. Then
equals 0.
equals 0 because you have ended up at the starting point. Is that the equation you've got? Right? So have you like any of you have any confusion? If you have any confusion, you can just ask me. Like
I draw the signs wrong here.
oh, okay. Yeah. So like if you start in any other node, you should have the, as I mentioned, you should have the same equation. So is it up to this point, are you okay?
So
Okay.
for the
Yeah.
resistors, would it ever be like minus I times whatever, or is it always plus?
So if we follow the direction of the current that we assume, the resistance voltage will always be positive. Okay, so from this equation, it should be I times 8, and it should be minus 40 plus 8. 32 on the other side. 4 ampere. Okay, so now calculate the value of VAB. That's your task. That would be pretty simple, right? The same rule of calculating V0 in the previous example. What would be that?
8.
Yeah, it should be 28, because like as I mentioned, if you go through the direction of the current, that should be the easier. Like we don't need to consider negative current, or the current is always positive. So the first one should be 5 times 4 I into R, then second should be the plus 8, and we end up here. So that's it. It should be 20 plus 8. So up to this point, are you clear? Like, do you have any confusion about KCL and KVL? So we can write KCL for a node if we know the current, and for a loop we can write KVL by assuming current if we don't know the voltage, and if we know the voltage, you can just apply KVL and write the equation, right? Okay, so up to this point we only considered KCL and KVL separately, like those are the simpler 1 loop, 2 loop circuits. Let's move to more complex circuits where we might have to apply all of those things. Okay. So this looks complex, but if we like do this step by step, if we solve this circuit step by step, this should be easier. And since we know all the rules, we also know all the formulas that you have learned before, we'll apply those. So this should not be difficult, right? So what's the problem here? Find the current values leveled in the following circuit. So what are the currents? This IT, I1, I2, I3, I4, I5. So we need to find out the value of these 6 currents. Yeah. So for this we will need all the concepts that we learned from the first class. We need the concept of equivalent resistance. We will need Ohm's law. We might need KCL and KVL, but let's see. But we will need equivalent resistance and Ohm's law, that's for sure. Okay, so let's you will do the calculation. I will just give you a hint. So first, when we try to calculate this IT, what does this IT represent? The total current that flows through this whole circuit. Forget about these. There are loops, right? There is 1 loop, 2 loop, 3 loop, 4 loop. That's what we counted at the very first slide. But forget about all these loops. Consider these as one circuit, because when the current flows, that's like one closed path for it. Right? For current, it always one closed path. So this when this IT flows and gets out from this voltage source, that's always see a one closed path. And the resistance that it sees, what is that? What was the idea of equivalent resistance? Do you remember?
Parallel.
So you can have like multiple, maybe like 100 resistors connected in series and parallel with a voltage source. What does that equivalent resistance of all those resistors mean? We always get one resistor, right? Is that correct? So let's draw here. So if we have like node A and multiple resistors, like 4 resistors between like A and B. So when you calculate the equivalent resistor of these 4 resistors, what do you get? One resistor, like right? One value. And where is that connected? Can we say that like this?
Yes.
The whole resistor network is represented by this one equivalent resistor. That is the idea of equivalent resistors, right? So, like, why we learned about calculating the equivalent resistor? Because, like, what do you care about? Like, when you see a circuit, or when we, like, for example, when you see a TV, what do you care about? Like, from the electricity perspective, what values are more important? Obviously, the electricity that it will consume, right? The first thing is like how much electricity will it consume, or how much bill you will need to pay for this. Okay, so that's calculated from the power consumption. We'll talk about the power consumption, but power is actually nothing but the voltage and current. And from any circuit, we can only measure voltage and current. Right? We never, like from a TV, we never measure the equivalent resistance of the TV. Only measure the voltage level. You see the 220 volt, something like that written in the chip, or the TV 205 ampere or some sort of current rating. So that's always voltage and current. But what's the use of learning to calculate the equivalent resistance? So the idea is here, if we consider this as node 1, for example, and this is node 2, and we have a huge resistor network here. From the equivalent resistance theorem, we can calculate the one resistance value that will represent this whole network. Is that correct? Right? So from these 5 resistors, we can calculate the equivalent resistors, and there will be one resistance. And why will that be connected between 1 and 2? And how will that circuit look like? Is that correct? And this equivalent resistor is the equivalent resistor of all this resistor network. Are you clear?
Yeah.
To this point? So that's why, like, we again, like here we are calculating the current of all the resistors. We don't do that in real life. What we do, we always care about the current that flows through the circuit. That's the most important thing. And for that, we need the equivalent resistor, because whatever resistor you have in that circuit, we will always represent that by one resistor. And if we now from this, what will be the current value? I equal to V by R, right? So we know the V here and R here. So for this, we know the Ohm's law, V equal to IR. So the current will be V equal to V by R, right? So if we know the equivalent resistance value, then the current, like that flows through the circuit, total current is simple, like voltage over the equivalent resistance. So that will be our IC. Is that right? So for that, to calculate this I2, we need to find out the equivalent resistance of this network. And you should be able to do that from the last class.
You can have some time to just calculate and then you can check.
Right.
So you're gonna give us some time to solve it and then check us.
Yes, that's what I will do. So you will first try to solve. When you are done, then I will solve. That will also help whoever could not solve. So let's try to find out the equivalent resistance of this resistor network. 5 resistors. you forget the formula, I can also write down the formula of parallel connection, right? Will be 1 over R parallel into 1 over R for R1 plus R2, and for series it will be RS equal R1 plus if you have multiple, that will be like that will go that.
So we have to come this. Oh, right.
I don't know that actually, so I'll have to slot that. So it should be 11.
The total current I'm talking about.
Oh, total current, yes, total current will be 12 ampere, yeah. So 132 by 11.
11 is the.
Yeah, 11 is the equivalent. Okay.
On over here, so that formula, see. Yeah. Series is the current, which is not.
Let's put it together. So as I explained for a long time that our idea or our goal is to represent this whole circuit like this. Right? We want to represent this 5 resistor network with a 1 equivalent resistor so that we can have this very simple circuit and we can easily calculate the current that flows through this circuit. So for that we'll have to first look at this portion here, A and C, between A and C. So are these two resistors connected in parallel or series? Parallel, because they are between 2 nodes. Here A and B are the same node. You can say B is nothing actually, is A. So they are between A and C. So if we use the formula of R parallel, it will be 1, 5, 2, 4 plus 1, 7. We'll be able to calculate the value of RAC. Right? So that should be 1 ohm. And similarly, now move to this portion here. Similarly, D, E, F are the same node because there is nothing actually. So we can call that as F, right? So these are eventually same. So these 3 resistors are between C and F. So they are also, all these 3 are also parallel. Right? So if we calculate the resistance between CF, that will be 1 over RCF is equal 1 over 60 plus 1 over 20 over 30. So from this we should get the value of RCF, that should be 10. So if we use this, then we should have something like this. We have one resistance between A and C, and we have one resistance between C and F. So our goal was to find out the value of equivalent resistance between A and F. So between these 2 nodes, these two are connected in series, right? So we can just add them. So the equivalent resistance of this whole network will be 1 plus 10, which is 11 ohm. Right? So that means this is our 11 ohm. And from this we can easily calculate IT actually. IT means V equal to IR, so V by R. 132 is the V and R is 11. So there will be 12 ampere. So do you have any questions up to this point? Are you good? So there is one tip for identifying which resistances are connected in parallel, which resistances are connected in series. Okay, so the thing is when the resistors are connected in parallel, all of those resistors will always be between 2 nodes. So if we count the number of nodes related to those resistors, they should always be 2. And for series, that should be more than 2.
Everyone got the right answer, Mohit? You understood the steps? So if I ask you, can you explain how you did it? Any of you?
Yeah.
Okay, Isan, go.
Okay, you did like the first one, because they were in parallel, like you're trying to make it all one resistor. So, and you do the equation, you get 1 ohm. And then the second one, the I3, I4, I5, trying to make that
Which
one.
equation we're following here?
The like 1 over,
Which type of connection is it? Parallel or series? Parallel connection.
yeah, and then I3, I4, I5, you make it 1 resistor, you get 10 ohms. And then 11 ohms, because they're in series now.
Or series.
Yeah, and then 132 volts divided by 11 ohms, 12 amps.
Adam, you got it? Adam? M? Shihab? Mohidin? Where are you? Then you got it, right?
Yeah, it's here.
Okay, I think we have some nays here, so we need more practice.
Yeah, sure.
This one's
Okay, so the next
This one is.
thing that I was talking about is like how we can identify what resistors are connected in parallel and what resistors are connected in series. So for this is simpler, right? But when you have like 100,000 resistors, like that might be difficult, but the rule is always same. So the resistors that are connected in parallel, the related nodes for all those resistances will always be 2. So here if we count, right, so this is like C, right? This is C, this is C. And as I mentioned, D, E, F are nothing but the same node, because there is nothing between D and E and F. So these are the same, we can call them D. So for this resistor, this is between C and D. This resistor C and D, this resistor C and D. So we always get 2 nodes for these resistors. So that's why they are parallel. And similarly, you can see here, these resistors are connected between A and C, right? And these resistors are connected between C and F. See, we have more than 2 nodes for these 2 resistors. And if you have another resistors, we'll have another node. So for series connected resistors, we will always have more than 2 nodes, the related nodes. But for parallel, we will always have 2. It doesn't matter how many resistors are connected in parallel. It might be 1,000, but the number of nodes related to all those resistors will always be 2. That's how you can verify that which resistors are connected in parallel and which resistors are connected in series. Okay, so now let's go back to the problem. So the problem was like to find out all the values of current. We have only find out the value of IT so far. Now we need to find out the value of I1 and I2. So as I mentioned, for parallel connection, the voltage should be the same. You remember that? Voltage should be same. That means the voltage of R1 and voltage of R2 should be same. Similarly, voltage of R3, R4, and R5, this voltage of these 3 resistors should be same. But the current will depend on the resistors. Okay. Since the resistors are all of the resistors are different, the current will also be different here. Right? So, but we need to find out the value of I1, I2. So let's try to focus on this portion first. So we know the resistance here. To find out the current, what do we need to know? That's always the triangle, right? Voltage, current, resistor. If we want to find one, we need to know the other 2. So if we want to find I, we must know V and R. We know R, we need to find out the V. As I mentioned, this R1 and R2 will have the same voltage. And what is that voltage? That voltage is RS, like AC, right? VSC, the voltage between A and C. Is that correct?
Yeah.
For these 2 resistors, the voltage will be VSC, and for these 3 resistors, voltage will be VCF. Okay? And we have this, so let's go back here. So we ultimately ended up here. So this is C. That was 1. That was right. So we ended up here before like completing the final step. So And this is our AC. So we'll have to find out VAC and VCF to find out the current of I1, I2 and I3, I4, I5. Is that clear? What do we need? Why do we need VAC and VCF? Is that clear? Because VAC, like this value of current I1, I2 will depend on VAC. And the value of the current I3, I4, I5, that will depend on VCF. Right? Okay, so to find out the VAC, we know that again, if we want to find out voltage, we need to know the current and resistance. We have the resistance. What was the current? 12 ampere. So we can easily calculate VAC here, right? That will be 1 ohm multiplied by 12 ampere. So that will be 12 volt. And VCF will be 10 times 12. 120 volt. Can you verify KVL from this? This is a loop, right?
Yeah.
I'm just checking. That's not part of this program.
Yeah.
But I'm just checking. We should be able to verify the KVL because that's the like universal law, right? So can you verify that here?
Yes.
So we know the voltage of this resistor is 12 volts. So if we start at A, we should first write 12 volt, then we should write 120 volt, and then we will get this negative first. So we should write 132 volt, then write 0. We have 0 on the both sides, right? So KVL is true here. So up to this point, we have the VSC and VCF. Now, can you tell me, like, what will be the value of I1?
V by R.
So, what should be the just tell me the equation? What should be the equation? I1 should be
V by R.
so which V?
V1.
VSC or VCF?
VAC.
It should be VSC, right? Because this network is about AC. So it should be VSC because, as I mentioned, like for both of the resistors, the voltage is same, which is VSC. That's why we calculated VSC. So for I1, it should be VSC by R1, which is 12 by 2.4. It should be 5 ampere. And I2 should be, what should be the equation of I2?
12 by 1.7.
12 by 1.7 because the voltage is same. You can calculate that. And for the second network, CF. So what should be the equation of I3, I4, and I5? For I3, which voltage should we use? VSC or VCF?
PCF.
VCF, because that's between C and F. So VCF by 60. That should be 2 ampere. I4 will be VCF by 20. That should be 6 ampere. I5 should be VCF by 30. That should be 4 ampere. So what did you get here? Like 12 by 1.7, 7 ampere.
7.
So now let's do one more thing. So the problem is like solved here. Like we found all the values of all the currents in this circuit. Now we have for I1 we have 5, I2 we have 7, here we have 2, 6, 4. Now let's again verify the KCL here, if we can do that. So since we know all the currents here, and this is also 12, since we know all the currents here, so first let's look at this A. So this should be A, right? All these 3 should be A node here. So if we look at this A node and we apply the KCL, what should be the equation? Do you remember KCL?
Yeah.
The current entering will equal to current leaving. So for A node, which current is entering?
I1.
IT, I1, I2. Like at node A, we have 3 currents, right? IT, I1, I2. Are there any other currents at node A? Only 3, IT, I1, I2. So which current is entering?
T.
Yes, you look at this, you just look at the direction here, the arrow, right? So IT is entering, so IT would be at the left and I1 and I2 both are leaving. Right, leaving node A. You look at the arrow, just there will be. So I1 plus I2. Now, if we see that IT is 12, I1 is 5, I2 is 7. KCL is verified. Similarly, if you look at C, at node C, so at node C, which currents are entering and which currents are leaving? So at C, we first find out how many currents are there. So at node C, how many currents we have? 4. So IT is like I1 plus I2, but if we like count them as individual, like I1, I2, then we have 5, right? I1, I2, I3, I4, I5. All of these currents are connected to C. So at node C, I1 and I2 are entering. Is that correct? Only I1 and I2 are entering, and I3, I4, I5, all these 3 are leaving. You can say that from the arrow.
But we can also say IT, right?
Yes, I1 plus I2 is IT. So yeah, so here you can just verify like 5 plus 7 and 2 plus 6 plus 4. So KCL is verified, right? So if you are lazy, right? If you don't want to calculate all the currents, right? You can, if you have only one unknown, right here, if you only can calculate I1, then you can just do KCL and you can calculate I2 without using this VSE by R2 formula, right? Because IT equal I1 plus I2. If you have I1 and I2, IT is just IT minus I1, because KCL always is true. Similarly here, if you have I3, I4, and you know like the IT, you can always calculate I5, because I5 will be IT minus I3 minus I4. Because the sum of these 3 currents will always be equal to the sum of the currents that is entering, which is IT. And these are the alternative way to solve this problem. Is that clear? So you can use all of those, KCL, KVL, and like Ohm's law, equivalent resistance. So in this formula, you used all of those actually. So yeah, so that's also, there's the solution of that as well. So like I mentioned like a little about power, right? So we actually care most about the power. That's related to voltage current, obviously, but from the high level, we always care about power because that's related to our electricity bill. Okay, so like, do you know the unit of electricity consumption? Watt is the unit of power, but electricity is like calculated in terms of watt hour or kilowatt hour, because we don't use watt hour. We use like some thousands watt hour every day actually. So that's why we like to keep that number smaller, we use kilowatt hour, which is like 1000 watt for 1 hour. So if we use an electric product that consumes thousands watt power for 1 hour, that will be like 1 kilowatt hour. Okay, so that's the unit of electricity consumption, and for 1 kilowatt hour we have a like dollar rate for that, and from that the electricity bill is actually calculated. And so the power is important because like the more you use electricity, the more power will be consumption, and from that you will have an idea how much electricity are you consuming every day, every month, every year. And then you can also check if the electricity that you are generating, like in your country or in the whole world or in a region, is that enough to support that electricity that you are consuming, right? So are you familiar with the idea of load shedding?
Yeah.
Are you familiar? Like the people that are from like Asia, India, Bangladesh, Pakistan, all that region, we are familiar with load shedding, but we don't have that here. So load shedding is done to like meet the demand of electricity, like electricity demand. So in our country, the electricity that we need is way higher than the electricity that we can produce. So what do? You do load shedding, like you like turn off the electricity for specific regions to like cut their demand. You always try to keep those two equal, that the electricity that you need is equal to electricity that you produce. For that, you need to cut down the demand. That's how, like, that's why load shedding is done. So the key point of this, all this is that we need, the power is actually important for any electric product, for any circuit, power calculation is important. So power is nothing but the multiplication of voltage and current. Okay. So if you take any element, right, a voltage source. So if we go to the previous example here, this is a voltage source. We know the voltage of that value and the current that is going out from this. So we know the voltage and current of this voltage source. If we know the voltage and current, we can calculate the power that is related to this element. Similarly, for the resistor, if we know the voltage and current of that resistor, we can calculate the power. So the formula is P equal VI. And as we know from Ohm's law, VIR, these three are related. So if you know voltage and current, you can use this. You can use this formula directly. If you don't know, for example, if you know only current and resistor, what do we know? Like V equal I into R, right? So that will be I square R. So if we only know current and resistance, then we can use this formula, P equal to I square R. On the other hand, if we know V and R, so if we know voltage and resistor, if we don't know the current, then we can calculate current from this equation, right? V by R, Ohm's law. So the power will be V square by R. So these are the three like interchangeable equations. If you know voltage current, you can use directly P equal V times I. If you know current and resistance, you will use I square R. If you know voltage and resistance, you will use V square by R. And the unit of power is watt here. Okay, so this is the like simple formula to calculate power, and there are two types of power. One is power supplied, and one is power absorbed or supplied power, absorbed power. So like what's the goal of using voltage source? So why do we use voltage source in a circuit? So what is the goal of this voltage source here? So if we didn't have this voltage source here, what would change? What would be the value of the current?
Zero.
What? So if we didn't have this voltage source, like there would be like short circuit, something like that, right? Nothing here. So that there will be 0 volt. So what should be the current here? 0 current.
Yeah.
Right. So the current is flowing due to this voltage source. So you can say like the voltage source is supplying that current. Right. So the sources that we use, voltage source, current source, those are for supplying that power to all the elements in that circuit or in that product, you can say. Okay, so like if you like connect this TV with a power socket, like that's the voltage supply, right? Power socket here is the voltage supply. So that's voltage source is actually supplying the current that the TV is using to turn on and operate at the next steps. Okay, so this voltage source and current source are like the power of those two sources are the supply power here. And absorbed power is like the power of the resistors in the circuit. Like there will be like with voltage source, there will be other elements like resistors and other things. So those elements will absorb the power that will be supplied by the voltage source and the current source. Is that correct?
Yeah, I'm just confused about the negative and positive.
Yeah, I'll come into that. So we only have supplied and absorbed power. So supplied power is coming from the voltage source and current sources, and absorbed power is being absorbed in the resistor and other elements in the circuit. Okay, so supplied power is always negative, and absorbed power is always positive. Why is that? So that's the convention actually. So that's the way of calculating power. Now, based on that, we have two equations, right? Plus VI and negative VI. So how should we know when we use positive voltage times current or negative voltage times current? So for that, we need to look at the polarity of the voltage and the direction of the current, because power is related to nothing but voltage and current. So the polarity of voltage and direction of current is important here. So you can see here, like if we look at this figure, first figure here, so is this current entering through the positive node or leaving through the positive?
Positive to negative.
The current is entering through the positive node or leaving through the positive node? Entering. Like you can say from the direction. So current is not generating from here. The current is actually flowing through the whole circuit. Actually, you can say something like, you can extrapolate that something like that, right? So the current is actually flow like a loop. That's not open. They're always closed. So you can say it here. So the current is entering through the positive node and leaving through the negative node. So that's why we use positive Vi. That's our absorbed power. If we have the opposite scenario, here you can see that the current is actually leaving through the positive node and entering through the negative node. Right? So for that case, we will use negative Vi, and that will be our supply power. So now if you go back to this problem here, this IT, is it entering through the positive node or leaving through the positive node? This IT here, is it entering through the positive node of this element or leaving through the positive node? Leaving, right? Because the whole path of this IT is something like that. This is going from this direction, traveling through here, and then again entering like this. So this is actually entering to the negative terminal and leaving to the positive terminal. So what should be this power? Supplied or absorbed? Supplied power, because this is leaving to the positive node and entering to the negative node. So for when we calculate the power of this voltage source, we should use P equal minus volt. P, that is 132, and I, which is 12. So that should be the power of this voltage source. Negative something. That means it's supplied power. And if we look at this R1 resistor here, so the voltage of this R1 was something like this, right? This was the positive and negative for R1, right? Remember the AC for volt, if we go to this here. So the voltage was for AC, the voltage was something like this, and CF it was something like this. So this was our positive polarity, and this was our negative polarity, right? For AC. So here if we mark that, it will be our positive polarity and it will be our negative polarity. Is that correct? So now if we look at the current I1, is it entering through the positive or leaving through the positive? That is entering through the positive, right? Entering through the positive terminal I1. So if it entering through the positive terminal, we should use this formula, positive. So remember, entering to the positive power, entering to the negative or leaving to the positive, the same thing, negative power. That's if you can just remember this, that if you have a negative power, that is supplied power. If you have positive power, that is absorbed power. Okay. Is that clear or is it too confusing? Just remember, like, which terminal it enters. If it enters to positive power. If it enters to negative power. Now, after you calculate the power, if the power is positive, that's absorbed power. If the power is negative, it's supplied power. Okay, is that clear? So we have another example. This is the last example actually. So here we will review all the formula, all the concepts that we have learned so far, like up to this point. Equivalent nature, Ohm's law, KCL, KVL, power calculation. So these are the 5 things we have learned so far, right? So in this example, we will review all those things. But before that, do you need any break? Okay, so we can have like 50-minute break. Sure. all the recording.
Yeah.
So the last example, this is like more simpler than the previous circuit actually, but we're just trying to review all the things that you have learned and concepts and formulas. So this circuit has three resistors, 10 ohms, 20 ohms, and 30 ohms. All of them are connected in series with a 12-volt battery, 12-volt voltage source. So we need to calculate the total resistance of the circuit. So I think we can actually solve this without pen and paper, right? So these three resistors are connected in series. So what will be the total resistance? That's the sum of these three resistors, 60 ohm. Then the circuit current. So what will be the total current that will flow through this circuit? 12 by 60, right?
60.
12 by 60 because voltage V by R. Total resistance is 60, so the 12 by 60, so it should be 0.2 ampere. And the current through is resistor. What should be the current through resistor R1, R2, and R3?
R1 or I1.
So what should be the value of the current? How should we calculate that?
V by R1.
Okay, but like, yeah, that's the way, but so that's all the resistance are connected in series, right?
So
So
60.
what's true for series? For parallel connection, we know the voltage will be same for all the resistors, but for series, what should be the same? Current, right? In series, like here, you see, like if you again think from the KCL point of view, this current is entering this node, leaving this node. Only one current, so this should be equal. If you look at this node here, this current is entering, this current is leaving. Are there any other current? Only one current leaving, one current entering. So this total current will flow through this, through all the resistors, right? So the same current will flow through the east resistor. Is that true, right? So for series, the current will remain same. So the three resistors are connected in series, so all the current that flow through these resistors will be same, and that's the total current that's flowing through this circuit. Okay, so the same amount, 0.2 ampere, will flow through this resistor, this resistor, and this resistor. Now, can we calculate the voltage drop across each resistor? So for these three resistors, we know the value of resistance, it's given. We have just calculated the value of current, which is 0.2 ampere, and that flows through all the same, all the three resistors. So what should be the voltage drop across each of these resistors? So here we have, like, first we have calculated the total resistance of the circuit. That was just the sum of all the resistors because they are connected in series, 60 ohm, right? So that was the first. Then second was the total current that flows to the circuit, which should be Vs, the voltage, divided by the total resistance, which is 12 by 60. That should be 0.2 ampere. Then the third question was to find out the current through each resistor, and that should be the same because, as I explained, all the resistors are connected in series. So that should also be I1 equal I2 equal I3, and that should be equal to IT, which is 0.2 ampere. Right? Now the fourth question is, what are the voltage drop across these resistors? Like we need to find out VR1, VR2, VR3. So formula is like V equal to IR, right? So for VR1, it should be the same current will flow, that is 0.2 ampere times the resistor 10, right? This must be simpler compared to the other, like the previous examples. So similarly, what should be the voltage drop across R2?
0.2 times 20.
0.2 times 20. 4 volt. Similarly, it should be 0.2 times 30. 6 volt, right? Okay, let's go back to the question. Like the next thing is like verify that Kirchhoff's voltage law holds true. So can you write the Kirchhoff's voltage law from this circuit? We know the current here. So you know the steps. So that will be a like review. So write the KVL equation for this circuit and verify if that is true from these 3 voltages. You already forgot the KVL. Kirchhoff's voltage law.
All the voltage is 0.
I'm looking at this row actually, so I want answers from this side. So have you forgot the KVL? So then please try to write the KVL equation for this circuit. So what's the first step to write the KVL? Identify the loops. There is one loop. And do we know all the voltages of these loops? Right now we know like the voltage of this resistor, and this resistor. Right? We know all the voltages. So we can just directly apply KVL. For that we need to find out or select a starting point. So let's start from A. So if we start from this, we will first see this resistor, and since we are going in the same direction of the current, so we should have positive, negative, positive, negative, positive, negative. So all the voltages of this resistor should be positive because we are going through the same direction of the current. So from the first resistor, we should write plus 2 volt, then we should write plus 4 volt, then we should write plus 6 volt. Then we are getting negative
12.
first, right? So we should write negative 12. And we are ending up at the starting point again, so we should write equal to 0. And if you see like true, right? So you don't need to remember anything, you just need to remember this, like the steps that we use to write this KVL. So if you can remember that, then you can like do anything else, all the other things. So you just need to remember the way to write the KVL, like the steps we learned together. So the final thing is like calculate the power of all the elements in the circuit. That's new, and you just learn that thing. So calculate the power of all the elements in the circuit and indicate if the power is supplied or absorbed. Okay. So up to this point, we have calculated the voltage of these 3 resistors, right? 2 volt, 4 volt, and 6 volt. And we also know the value of this current IT. There was 0.2 ampere. So if we know the voltage and currents of all the elements, we can calculate the power, right? P equal to VI. We just need to find out will that be positive or negative? That's the thing. So can you calculate the power of all the elements? So first, let's calculate the power of Vs. So P of power of Vs, that should that be positive or negative?
Positive.
So how did you say that? Like, can I explain for others?
It's going in the positive direction.
which like for the power, the convention was if the current enters through the positive node, positive terminal, that should be positive power, right? If the current enters through the positive terminal, that should be positive power. So for Vs, is the current entering through the positive terminal or leaving through the positive terminal?
Enter.
Negative, right?
Entering to the negative. This is the current, right? This is the direction of the current, you see. So this is leading to the positive and entering to the negative for Vs. Is it clear? So is it not? It's not entering to the positive. So if it's entering to the, remember this, if it's entering to the positive, that should be positive power. If it's entering to the negative, that should be negative power. Okay, so this is entering to the negative terminal. So this should be negative V times I for Vs. Is it clear? So first the voltage for Vs is it's 12, negative 12, and current is 0.2. So you can calculate the power. That should be
Use the watt as an unit.
yeah, that should be negative 2.4 watt. So now next element is R1. So what should be the power of R1? Should they be positive or negative? It's the same rule.
Negative.
Negative. Why?
It's the opposite.
The current is entering to positive or negative. R1 for R1. Just look at this one here. And positive and negative are marked.
Current is coming through the positive to the negative, right?
You can see that like the current, this is the direction of the current here. Yeah. So the current is entering to the positive, leaving to the negative for R1. And same for R2, same for R3.
Or positive.
Right? So for R1, R2, and R3, all should be positive V times. Is it correct? So for R1, V is 2 and I is same. Okay, so it should be 0.4 watt. Similarly, for R2, it should be 4 times 0.2, it should be 0.8 watt. For R3, it should be 6 volt times 0.2 ampere, which should be 1.2. 1.2 watt. Is that clear to this point? So these are the power consumptions for all the elements in this circuit. So from this, which one is the supplied power and which one is the absorbed power? Can you identify that?
So negative is supplied,
Yes.
positive is
So
absorbed.
negative power should be the supplied power. So there is only one supplied power. This is the supplied power, and all these three are the absorbed power because they are positive. Okay. Is that clear to this point? So now we'll talk. So that's the end of like learning all the theories for this program actually. So you have learned the Ohm's law, equivalent resistance, KCL, KVL, and power calculation. So these are the 5 formulas or equations you can say, and how we can use those in circuits. That's the aim for that. And this is just like again another concept. So the like electricity that we use, so that can be of 2 major types. One is the DC and AC. So far the voltage and currents that you have used in different examples or in different circuits, was that constant or was that changing over time? That was constant, right? When we used 12 volt, there was always 12 volt, right? That didn't change over time. So you know switch, right? When you turn on the switch, this 12 volt will always supply 12 volt of voltage or the equivalent current. That's like calculated from this resistor or other like elements that are connected. So after you turn on the switch, it should always supply 12 volt. And if you turn off, that should be 0 volt, right? So that's constant after you turn on the switch. That doesn't change over time, and that's what we get from batteries, right? We call this direct current, or in short DC. Okay, so you can see here it is represented like over time. If you turn on the switch, it will always remain constant, and it will supply a fixed amount of voltage. If that's 5 volt battery, it will always give you 5 volts. If that's 12 volt, it will always give you 12 volt. There is another type which is alternating current, or AC, where the scenario is different. The polarity is alternated. Okay.
Dr. Fatima wants to take a break because the food's here. You guys want to take another break to eat?
And finish this concept.
Yeah, you can do that, sure. So for AC, the scenario is different. It doesn't remain constant over time, but it changes over time, and changes in a way that it switches its polarity. You can see here. So for this portion, the voltage or current is negative, and for this portion is positive. Same thing, negative and positive. So that's a period related to it, right? So we know the period, frequency, all those things from basic physics, right? So what's the period? Like if we mark this as T1, T2, T3, T4, what's the period of this like oscillate? This is like oscillation, right? So this oscillating signal, what's the period? So this is T1, this is T2, this is T3, T4. What should be the period? So from this, if this is 0, so from 0 to T2, we have one, say, like you have that the thing that you have from 0 to T2, the same thing repeats, right? So period is defined from where the repetition starts up to that point, right? Like one oscillation or one, like you have the idea of frequency and period, right? So here 0 going to negative, then you have another 0 here, but it's going to positive. So that's, these two are not the same point, but this is 0 and going to negative. So this is the same point. So from this point to this point, T2, that's your one period. So for AC, we have a one period, and we know the frequency is like inverse of the period, right? 1 over the period is the frequency. So and you can see like in one period, you see that there is like two half, we call them half cycle. So in the first half cycle, if it's negative, in the second half cycle, it will always be positive, or vice versa. If in the first half cycle you have positive, then in the second half cycle it will alternate its polarity, it will be negative. That's the idea of AC. And what, like, which type of electricity, like DC or AC, which one do we use, like in homes or like televisions?
AC.
AC. Why? Is DC better or is AC better?
AC.
Why? That's the question, right? So, like from the high level, like you see that like over time, the DC signal does not change; it remains constant. But AC, it changes. It should be problematic, right? If it changes over time, shouldn't that be? If you have a constant supply, shouldn't that be better? Yeah, that should be better. Like from that perspective, DC is better, but there are other things, right? So, like that's why we use DC as well, don't we? Like mobile battery, right? That's DC. So whenever we can use electricity, like in that location, we use DC because DC is always better than AC. But if we need to transmit that, if we need to transfer from electricity from one place to another, then we need AC. Okay, so that's what we do. Like when we use electricity in our homes, do we generate electricity in our homes, or do we get that from other places?
Other place.
other places. So we have like power plant to generate the electricity. We have power grid to store the electricity, and then we have different distribution transmission network to to supply that electricity to our homes so that we can use that. Right. So whenever this transmission and distribution is related, AC always win. Because like as I mentioned, like when you distribute electricity through a wire, like that's what we use through a wire. Wire has a resistance. So resistance will take a voltage, right? If there is any resistance, if there is current flow, there will be some voltage. So V equal to I. So the voltage that you supply from the power station, if you use DC, the voltage will drop across all those wire resistances. And the voltage that you get, the further you take that, the less voltage you will get. So maybe you need 12 volt, you supply 12 volt from the power plant, or like the place where you are generating the DC volt, you might not get 12 volt in your home because that will drop across the wire resistances, right? So that's what. So when we use AC, what we do, we actually increase the voltage. So the voltage that we use in our homes, that's around 200, 220 volt, right? But when we first supply the voltage from the power grid, that's in thousands of volts. Okay, thousands of volts. So if that even losses on wires and resistances, AC signal has also losses. Similar thing DC. But if you start with 1000 volts, how much that can lose, right? So we will still have some like hundreds of volts, right? After losing the wires, if you even like distribute that through hundreds of kilometers. Is it clear? So we can actually increase the AC, and when we get the voltage in before our home, there is a transformer, like transformer. So transformer is actually responsible for increasing and decreasing the voltage. Because that step up, step down. So with the transformer, we first step up, we distribute that through wires. We go to the transformer near the home. We then step down, like whatever we may be getting like 500, 600 volts of signal. We step down that volt to 200, 220 volt, which is suitable for the electric products. Then we use that in our home. So now the thing is like this transformer don't work with this. That can only work with AC signals. That's why we use AC. Only because of that, like transformer, the ease for the transmission and distribution. Okay, but whenever we can like use like locally generated voltage, like mobile phone charging, we use DC. Because that's better. Like that always gives you a constant amount of current. That's better for your products. Like instead of like pulsating positive negative current. Because if you have a voltage positive negative, current will also be positive negative, just divided by resistance, right? So that's why like from the current perspective, the DC is always better because that's constant. But for distribution transmission, the AC always wins. There was like famous fight between Edison and Tesla. If you just Google that, Tesla and Edison, right?
Yeah.
Two famous scientists. And like one was in favor of DC, another was in favor of AC. So there was a like big fight. They also like both of them had like their own companies. So if you just Google, and you should know about that. So that's about like DC versus AC. And till that we use AC, and again locally generated electricity we use DC. So that's just a like explanation thing. And so okay, then we can have that break, and after that we'll have. So, as I mentioned, I will now discuss how we can use simulators, like tools that is developed for circuits, like simulation or solving. How we can use that. So there are like many industry standard circuit simulators like Cadence, ASTEP. So hopefully you will use Cadence at the end of this program, like to make some layout. Like the Cadence is used for like chip design and all those things. You can prepare the physical design layout there, and you can submit that to the foundry or any industry that fabricate chips. So you can get the chips back. So you will use Cadence, but ASTEP is another like powerful software that is used for only circuit simulations. You cannot do physical layouts there. We typically use that for our research. So you will have some idea how to work on Cadence. And we also have these are not free, Cadence and AC Spice, these are industry standard tools. But we have some free tools like LT Spice. So Spice is a family actually. Spice is a family of tools that you can use for circuit simulation. AC Spice is the most powerful member of the family, and LT Spice is one of the members. That's also powerful, but you can use that for free. And you can download that in your computer, and you can use that. And we also have some online free tools like Tinkercad, Circuit Lab. There are many others. If you just search free circuit simulators, you will have a lot of tools there. I just mentioned two, and for this class we will use this Circuit Lab tools here. And so I will just show how we can use the same circuits that we have solved in pens and papers, how we can solve the same circuits in the simulators. Okay, so you'll have to first go to file and open a new file for the circuit. So if you use this, you can you can see that here the power is also limited. You can see here you have all voltage and current sources under the DC sources. You can see that right here. Sure how to do. You cannot turn on the laser pointer here. This is the power point. So you can see here this. See the DC source here in the left. Are you seeing that? Yeah, so in DC sources, you have voltage and current source that we used. We have resistors, capacitor, inductors. We will learn them later. We have other these are the AC sources that I discussed. It's AC voltage, AC current, all those things. We have other components that we have not learned yet. But I think for up to this point, we only need voltage resistor, and another thing so in the circuits that we have solved so far, the negative terminal of the voltage, right? So let's go back. So if you look at this circuit here, the negative terminal of the voltage is actually the ground of the circuit. So for any electrical circuit or for anything that where you use electricity, electric voltage, current, you need a ground, right? So ground is, you can say ground is the reference. Ground means 0 volt. So if here this is the ground, okay. So in every circuit you need a ground, and that's the reference. So ground is actually 0 volt. So when you measure measure the voltage of a node, if you try to measure the voltage of this node, maybe VB. So what will be the other point? That this ground will be then the reference. Okay. So when we say that the voltage of this source is 12 volt, what's the reference? This reference is the ground. But in our circuit, we typically do in the theoretical circuits, we don't typically show the ground because this negative terminal is is always considered as the ground. Okay, but when we go to these simulators, we will always have to use ground, and you see this is the ground here in the left, in the top left, right? You see this is the ground, GND. So this is the ground. So you'll have to use that. This is the only difference that you will see. Now let's do the same circuit that we did at the end. 3 resistors. There was 3 resistors, right? 1 voltage source and 3 resistors. So in that circuit, we had if you have drawn the circuit, so we had 1 voltage source. So how to use this? So you just have to select the element that you want to use, and then you just have to over to the canvas. This is your canvas. Over to the canvas and just click, it will be placed. Okay, so this is your voltage source, but the voltage was Do you remember the voltage was 12 volt, right? The voltage source had 12 volt. Yeah. So if you right click this, you can just edit parameters, click edit parameters, and you can change the value of the voltage source. You can just mention 12 here and press enter, it will be like 12 volt. Okay, so then we had 3 resistors, right? 3 different resistors. Just click resistor and hover and click again on the canvas where you want to place it. Yeah, so and we need a ground, as I mentioned. The ground will be connected to. We need a ground for every circuit. So now we need to make the connection between all these elements because like this is currently open circuit, right? There is no connection between, there is no closed path. So we need to connect all these elements. So for that we need to use wire. You see this wire, you need to click it. And then if you hover to the any element, like at the end of the element, you will see this node. So you need to click on this node, and if you just I don't have the mouse, that's why.
Which one is the wire
Sorry.
which one is the wire you're collecting?
Yeah, I'll show that.
So,
Let me delete this first. So there is one wire like at the top left.
Oh, okay,
This is the
fine, I got
palette
it.
where you will have to bring the elements from. So there are all the elements. So this is the wire. You have to select and then you'll just click and then click and hover. Click and hover. We need to we want to connect it here, right? It will be connected here. So just click it again. It will be connected. Then we need to connect this. So we need to select the wire again. We need to connect these 2 resistors. We need to connect wire. Click wire. Connect these 2 resistors. We need to click wire. Connect this with the voltage source here. And the ground should be connected to the negative terminal of the voltage, as I mentioned. Okay, so this is the circuit, and the resistance values, if you remember, right click edit parameters. The resistance value, the first one had 20 ohm or 10. You just type 10 here. It had 20, right? Just right click and edit parameters. Write the values in this R section here. Press enter. Okay, so this is the circuit you had. We solved. What did we solve? We solved the current through each resistor, right? So if you just current through each resistor, voltage drop of each resistor, and also the power of each resistor, right? So if you just now put your mouse over the resistor, it will show all the information here. Can you see that? Is it visible, right?
Why is it like megawatts?
Not megawatt, it's milliwatt. Small m means milli. So we had 0.4 watts, right?
Yeah.
0.4 means if you multiply that by 1000, that will be like in milliwatt. So 400 milliwatt. So the voltage we had 2 volt, right? That's what it's showing, 2 volt. And current was 0.2 ampere, which is shown here like 200 milliampere. Right? Now if we put the mouse on the resistor 2, it should show its like power, voltage, and current. Same thing for R3, it should also show. And if we put the mouse, you see the power is negative here. And the power of all the resistors are positive. And that's what we calculated, right? The resistor had absorbed power or positive power, and only the voltage source had the negative power, which was the supplied power. And also you see the current that is flowing, that's negative. You remember the current was flowing, leaving to the positive terminal and entering to the negative terminal in the so I can actually do that just. That's where we actually discussed. So you see the current here is actually leaving to the positive terminal and entering to the negative terminal. So when you see the current of this voltage source, there should be there should be negative current. That's why it's showing negative current. Positive volt is 12 volt and power is negative. You see the 2.4 watt supply power. Is it clear? So that saves a lot of time, right? You just need to build the circuit and you can just,
How do you do the arrow for the current?
sorry.
The arrow for the direction of the current, how do you differ? There's one, it says current sources is going downwards. If I want to make it upward.
Yeah, I'll show that. So yeah, I'm showing another example. Okay, so that's like simple the simple circuit. Now, if you want to make the more complex circuit, the circuit that we
If you
Dr.
guys have
Alia.
laptop, the link is in the classroom. You can go to the website, Circuit Lab. Google Classroom, the slides shared.
Also, I shared the slide. Yeah,
22, yeah.
yeah. In that,
If you go to slide number 22, there's link.
I'll delete
The
all
Circuit
this.
Lab, last one. We should bring laptop from next class. This.
So not sure. Like, even,
Could we do
like, maybe
simulation?
we can actually mention on the announcement as well. Like when we share the slide, that depends on the topics that we cover.
Yeah. It is.
I'll just show another example. With this, like the complex circuit that we solved, like 5 resistors and like with one voltage source. You remember that had like, we'll try to make the circuit the same way that was in that drawing. Okay, so we need one voltage source. So we need to rotate that, right? That had like, easier if we could draw that.
Find it, Mahdi?
I could do something like that, right? So just look at this structure. Okay, so we'll try to make the circuit like exactly like that. So we'll have to rotate this. So if you right click, there is like different rotate options. Rotate clockwise, rotate counterclockwise, flip horizontally, flip vertically. So for that we need to rotate it counterclockwise, and that will look like the voltage source that we need. So and the volt value of that was 132 volt, I guess. So if we just right click, edit parameters, and if you can just write 132, it will be 132 volt. Okay. So then we need 2 resistors to make the parallel connections, and we need to rotate that as well. So rotate clockwise. Here we need another one. Let's rotate it clockwise. Put it here. We need 3 more. So,
You say Ctrl V.
we can. I think we can also use that. Here. Yeah, we can use that as well. It will like put one on top of another,
Each other,
so
right.
you'll have to be careful for that. And just now we need to make connection. Also, we need the ground here. If you don't put the ground in the circuit, then it will not show any result. It will show some errors. So now we need to make the connection. So where it was connected to this, these 3 were connected together. So let's put here. complete, right? So there was the circuit. We have 5 resistors. Now we just need to change the values of the resistor. You can go to 8 parameters. What was the value? It was like 2.4, right? 2.4 plus 1.7. What is the value of this?
2036.
60.
2036.
2036. Okay. Oh, it changed. Okay. So now again, if you just like put your mouse on the resistor, it should show the voltage and current. Okay, you see the current is showing negative, right? Negative current. Should it be the case? We calculated positive current for the for this all these resistors, right? Do you remember? We calculated positive resistance for all these positive currents for all this resistance, because so the thing we did wrong is to like when we rotated the resistor has a predefined positive and negative. So we only rotated one. So what we did like this is now the negative terminal of the resistor, and this is the positive terminal of the resistor. That's why you also see negative voltage, but we should see positive voltage. So for that we need to like just flip horizontally. Now if you put mouse on that, you see there is, you see the current is positive. So when you rotate, you need to like make sure that you rotate 4 times, or you can just rotate once clockwise and then flip horizontally. That will do it. So you need to like, so this should be your positive terminal of the resistance, right? Because the current will flow this direction. The voltage or the positive terminal of the resistor should be here. You need to make sure that. So when the resistance was like this, the top one is always positive and negative, the bottom one was the negative. So when we rotate clockwise, so what we did, we negative came here, so it became negative, and the positive went to the right side. So we cannot do that. That's why the current, also you can see that here, the current and the voltage that we are getting is negative. Yeah. Because we did the same mistake for all the resistors. So for all the resistors, we need to just flip horizontally. Now you see like it shows positive and negative values. Okay. I think that's all for today's class. If you have any questions about what we have
You have
covered
to be a circuit member to do it.
Sorry.
It's free.
You can just
Sign in.
create an account. Create an account.
Create an account.
Yeah, that's free. You just need to like provide your email and you can set your password and then it becomes free. And you can also like simulate some circuits without logging in. But if you want to like do many like multiple circuits in one run, then they will tell you like you cannot proceed without logging in. So you need to create it. So this is one way to verify the results that you got like on papers, and like we are thinking of giving you some exercises or homework type things, or maybe like we will talk about that. Like when you like for that you cannot use these tools, right? We will need the equations that you use, like KVL, KCL equations and hand calculations for that. And then what you can do, you can just verify your results. Like the results that you get from your hand calculation, you can just verify that through the circuit simulator. Right? So and also like these are like useful when you like design circuits, right? Like when you hand calculate, like if you are not sure about the values of these resistors, like in hand calculation, you cannot do that. Like you cannot use different values of resistors and calculate the same thing again. Like that will be extremely time consuming, right? But here you can just easily change the values of the resistor, right? And you can see how that affects the currents, voltage, and all those things in the circuit. Right? So these tools are extremely useful, and yeah, and you can also like use this for like making different circuits, and how does that behave, how the current and power looks like in different circuits. You can do that in the system.